I'm Seonggyun, a co-first author of this paper. Today, I'll introduce my research, MiDAS, to minimize write amplification in logo-structured systems. This research has been conducted in collaboration with DGIST, Virginia Tech, and Gyeongsang National University. So these days, logo-structured systems are widely used in various applications, including key value stores, file systems, and storage firmware. However, in logo-structured systems, garbage collection overhead is a significant problem. During the GC, the systems copy the valid blocks into the free space to ensure there is more enough free space. This causes additional writes denoted by GC write. Typically, write amplification factor, WAF, is used to represent this GC overhead. Then, how can we reduce WAF in logo-structured systems? A common approach to reduce WAF is a data placement, which involves grouping data blocks with similar invalidation time together. If blocks with similar invalidation time are grouped together, when a certain period elapses, the blocks within the group are invalidated around the same time, preventing unnecessary data copies by GC. Therefore, it is essential to group data blocks with similar invalidation times together. Then how do we group the data blocks? Data placement techniques utilize estimate invalidation times to determine the hardness of data blocks and group those blocks based on their hardness. Here, hardness refers to the duration of the invalidation time. For example, a block with a short invalidation time is treated as hot block. Then one pivotal question arises. How do we optimally design data placement to minimize WAF as 1? Then I'll explain what might be considered an optimal data placement. To achieve optimal data placement, 3 conditions must be met. First, the optimal algorithm should accurately predict block invalidation times, and blocks are categorized by their hardness, which we will denote using colors for the purpose of this presentation. This means that blocks with the same color exhibit similar invalidation times. Second, the optimal algorithms determine the number of groups according to the number of colors. The number of colors means the number of clusters with similar invalidation times. After then, based on their colors, incoming blocks are placed into their designated groups. For example, the hardest blocks as denoted by red color are placed into the first group, group 1. Then the following blocks are also placed in the appropriate groups. Then at some point, a specific group may reach its capacity, making it impossible to accommodate any new blocks. If the blocks within that group have not yet been invalidated, unnecessary data block copies may occur, despite the blocks being accurately grouped together based on their hardness. So the optimal algorithm must also determine an appropriate size for each group to ensure it offers sufficient time for block invalidation. The group size represents the maximum number of blocks that can be accumulated within the group. If each group is allocated a larger size than previous size, more blocks can be accumulated into the group, delaying the point at which the groups become full and triggers GC. So this sufficient size ensures a longer invalidation time for the blocks. So in summary, to achieve the optimal, we must check this wish list. First, predict invalidation time accurately. Second, set an appropriate group number. And third, set an appropriate group sizes. If we can design the data placement by following this wish list, it can be optimal. Next, we evaluate whether existing techniques follow this wish list. Unfortunately, we found that SOTA techniques fail to achieve optimality. So we analyzed why previous approaches failed to reach the optimal. We aimed to compare existing techniques with the optimal. However, implementing the optimal for each workload is NP-complete. Instead, we utilized an Oracle algorithm, ORA, that mimics the optimal, demonstrating sufficiently low WAF. We compared ORA with SOTA data placement techniques, including CAT, AutoStream, MiDAS, and SetBit across YCSB-A and Barmail workloads. ORA achieved a WAF close to 1, significantly outperforming the existing techniques, which exhibit WAF at least 2.1 times higher than ORA. We analyzed why this gap between ORA and SOTA occurs. First, SOTA techniques often inaccurately estimate block invalidation times, relying on methods such as utilizing the latest update interval or block age. The latest update interval refers to the time elapsed since a block was last updated. CEPIT assumes that block being written now will be invalidated after the same interval. On the other hand, age measures how long a live block has existed up to the present. Both MiDAS and CEPIT work under the assumption that if a block has existed for a certain period, it will likely continue to exist for a similar duration. So we analyze the accuracy of these methods in predicting invalidation times. The x-axis of this graph represents the actual hardness of data blocks, while y-axis quantifies prediction accuracy. So as anticipated, Aura demonstrates the highest prediction accuracy. However, the update interval methods reveal lower accuracy for colder blocks, and conversely, the age method shows lower accuracy for hotter blocks. So we found out that current technique fell short of meeting the first requirement for optimal data placement. Second, most existing techniques fail to find the number of groups. SOTA techniques set a fixed number of groups. For example, CEPIT maintains 6 groups and MiDAS maintains 8 groups. Also, they do not dynamically adjust the number of groups according to the workload patterns. This approach contrasts with an optimal approach that supports a suitable number of groups according to workload patterns. As a result, the second element of wishlist is not addressed in SOTA techniques. Finally, most existing techniques fail to find the proper group sizes that minimize WAF. The graph shows whether each technique applied the proper group size of group 1. The star mark represents the lowest WAF point, and the circle mark represents the actual group 1 size for each technique. So in the case of Aura, it applies the best group size and provides the lowest WAF. However, MiDAS and CEPIT set smaller sizes, which increase WAF. So we checked that the existing techniques do not also follow the third element of the wish list. So in summary, the primary challenges include inaccurate prediction of block invalidation times, a lack of consideration for the appropriate number of groups, and insufficient attention to group sizes. Here, we define the number of groups and their sizes as group configuration. So to reach the optimal, it is important to address these issues comprehensively by following the outlined wish list. So to overcome those limitations, we designed MiDAS. First, we established design goals that adhere to the wish list, and based on these goals, we developed MiDAS. So our first design goal is how to accurately predict the invalidation time of data block. Unfortunately, we already have some hints. As seen in the previous result, each method shows different strengths in prediction depending on the data block's hardness. For example, in case of update intervals, there are high accuracies for hotter blocks, while for age, there are higher accuracies for colder blocks. Therefore, for accurate prediction, our design needs to utilize different prediction methods depending on the block's hardness. The second design goal is how to find the best group configuration. Here, what exactly is best? We will define best as what can offer the lowest WAF. Therefore, to find the best group configuration, we must be able to predict the WAF for various group configurations. Then how can we predict the WAF? Maybe we need to model our systems to simulate data movement and analyze the workload patterns to find the trend of data movement. By doing so, we can predict the WAF and find the best group configuration. Here is a design overview of MiDAS based on 2 design goals. To achieve the first goal, MiDAS predicts the block invalidation time using both update interval and age according to block's hardness. And to achieve the second goal, MiDAS added system model and workload pattern analysis. MiDAS proposed Markov-Chain-based Analytical Model, MCAM, and update interval distribution, UID. So using this WAF prediction system, we can evaluate the WAF for various configurations, find the best one, and apply the best one as a group configuration of MiDAS. So let's take a look at details. First, for accurate invalidation time prediction, we utilize the latest update interval for hot block separation, which is the method that CEPID adopts. For incoming blocks, MiDAS separates the data blocks into hot or cold. And the hot and cold blocks are separated by the invalidation time threshold. MiDAS considers data blocks with invalidation time shorter than invalidation time threshold to belong to the hot group. We call this threshold as the hot-cold threshold. However, we don't have any insight of which one is the best hot-cold threshold. This problem is not also considered in existing techniques. So, in addition to finding the best group configuration, we also need to find a hot-cold threshold that can minimize WAF. For cold block separation, we utilize MiDAS concept, which is the cold block separation techniques using age of a block. Actually, MiDAS separates data blocks based on the migration count. A high migration count means that the block has lived a long time in the system while being valid. It implies that the age of a block is proportional to each migration count. So in MiDAS, data blocks are only migrated into the next group in the chain by GC. The second design is related to the find the best group configuration and hot-cold threshold. First, we propose MCAM for simulating data movement in the system. Because the design of MiDAS is based on the chained organization, it can be modeled as a Markov chain. MCAM allows us to simulate data movement and predict the WAF. However, MCAM alone cannot fully predict the WAF because it does not know how much data move between groups. That is, the transition probabilities between groups are required to predict the WAF. So to obtain the transition probabilities, we need to know the workload patterns. Therefore, we also propose the update interval distribution UID for incoming blocks, which reflects the workload patterns. MiDAS predictably monitor workload and generate UID. With this UID, we can estimate the ratio of data movement between groups, that is, transition probabilities. It allows MiDAS to predict the WAF for a given hot-cold threshold and group configuration. By using this WAF prediction system, we can identify the best combination of hot-cold threshold and group configuration by evaluating the WAF for various combinations. I show the example. For any possible combination, MiDAS predicts the WAF. And if the predicted WAF is sufficiently low, we apply this hot-cold threshold and group configurations into the MiDAS system. If the predicted WAF is not low, MiDAS evaluates the new combination and repeat the process until finding the combination which can provide sufficiently low WAF. This is the overall workflow to find and apply the best combination into system using our WAF prediction system. Then I'll briefly explain how to predict WAF using MCAM and UID. There are two main components in MCAM: stage and transition probabilities. First, in MCAM, blocks can have two types of stage: free or one of the stages from hot to GN. A block in the free stage indicates that the block is invalidated and ready to be reclaimed for the future write. Blocks in the stage from hot to GN are considered valid within their respective groups. Next, the transition probabilities represent the movement ratio between those stages, and it can be obtained by using UID. Then I'll explain how to predict WAF using MCAM. First, the initial state is set such that all blocks are in the free state. Here, the only assumption is that blocks in the hot state are always invalidated within the hot group. This means the transition probability from hot to G1 is 0. From the initial state, we proceed with a step update of MCAM. A step update is the process where blocks move to different stages according to their transition probabilities. Here, free blocks are moved according to the transition probabilities from free to hot and from free to G1. These step updates are repeated until the number of blocks with each stage converges. Then we can predict the WAF using the converging number of blocks in each state from hot to GN. Recall that the WAF value can be calculated through the amount of user write and GC write. In MiDAS, user writes are only placed in the hot and G1 group. So the number of blocks in the hot and G1 state represent the amount of user writes. On the other hand, data blocks migrated by GC are placed from G2 to Gn. So the amount of GC writes equals the sum of the number of blocks in the G2 to Gn stage. Therefore, we can use these values to predict the WAF. The remaining issue is we need transition probabilities to predict the WAF using MCAM. So we utilize UID, which represent the workload patterns. And by using UID, MiDAS can predict the transition probabilities. So UID is update interval distribution for incoming blocks into system. And UID can be generated by monitoring the incoming blocks. This UID provides probabilistic statistics on what update interval a block will have. The x-axis of this UID means the update interval, and the y-axis means the probability that a block have a certain update interval. I want to explain how to estimate the transition probability using UID, but due to the time limit, please check our paper how to estimate them between those groups and subsequent group. So using MCAM and UID, MiDAS can predict the WAF for a given hardcore threshold and group configuration. Although not covered in this presentation, there are two remaining issues. First one is how to efficiently find the best combination of hardcore threshold and group configuration. For time and computation efficient finding process, we take a greedy approach instead of evaluating all possible configurations. Second one is how to deal with occurred changes. MiDAS periodically generate new version of UID and find the new best configuration for changed workload parent with low overhead. For more detailed explanation, please refer to our paper. Then I'll explain the evaluation of MiDAS. For evaluation, we target the low-structured system as flash-based SSD. We implemented MiDAS on FPGA-based SSD prototype. Then we evaluate MiDAS under various workloads, including file bench, YCSB, TPGC, and production workloads such as Alibaba Cloud and Microsoft Exchange. For comparison, we implement 4 SOTA GIST techniques. We focus on 3 key objectives to evaluate MiDAS. First, we evaluate if MiDAS effectively reduces WAF compared to other SOTA techniques. Second, we explore how MiDAS achieves the WAF reduction. Finally, we evaluate the overhead of MiDAS. First, MiDAS shows reduced WAF compared to other techniques. This implies that MiDAS effectively finds the suitable hardcode threshold and group configuration. On the other hand, in case of the Alibaba workload, a significant WAF reduction was not observed in MiDAS. There are 2 main reasons. First, Alibaba workload trace was too short to gather enough information to generate a UID. And second, the Alibaba workload exhibit irregular I/O patterns. Nevertheless, as I explain later, MiDAS show better results in terms of throughput in the Alibaba workload, despite having similar WAF. Second, we analyze the impact of the individual design component of MiDAS, that is, hot block separation for accurate prediction denoted by plus hotset, and applying the suitable hardcore threshold and group configuration denoted by plus group conf. To observe the effect of adding each component, we start up with MIDA, the basic design that MiDAS takes from. As can be seen from this result, each factor plays a very important role in reducing WAF. Each component shows 12% and 31% reduced WAF for plus hotset and plus group conf compared to the baseline. Finally, we analyze the throughput and CPU overhead. MIDAS shows higher throughput compared to SOTA technique. It is because MIDAS not only reduces GC overhead, but also requires a low computation to run. As mentioned earlier, MIDAS and SEPBIT exhibit similar WAF in Alibaba workload. However, MIDAS achieves a higher throughput compared to SEPBIT. To understand this region, we analyze the CPU utilization for each technique. The CPU utilization graph indicates that SEPBIT requires high CPU usage to run each algorithm. Meanwhile, MIDAS maintains CPU utilization level comparable to MIDA and shows lower utilization than SEPBIT. Here is the conclusion. We analyzed the limitation of existing techniques, and we proposed MiDAS to mitigate GC overhead by overcoming those limitations. The experimental results showed MiDAS achieved reduced WAF, improved throughput compared to existing technique with low overhead. This is the end of my presentation. Thank you.